Okay, so jumping right into it, this homework seems to primarily focus around graphs, namely the algorithms applied to graphs, breadth first search, and depth first search. So the first one here, they said for the following graph, give the breadth first search results of steps of the algorithm by giving the sequence of states of the queue, the list of vertices, before next iteration of the while loop. Each vertex should be given in the form vertex number, distance, and parent. So for example, the queue element S3T should mean that vertex S was discovered at a distance 3 from the root, and it was discovered from vertex T. So this means we need to keep track of the parents so we know which node discovers each of the subsequent ones. And then here they say, assume that the graph is given by its adjacency list representation, in which the edges of every vertex are ordered by the numbers of the n vertices. Okay, so the adjacency list representation isn't entirely important. That's just a way that graphs can be represented. You can have them represented as an adjacency matrix, so you have a full matrix that'll show all of the edges from nodes to nodes. You can have a adjacency list representation like they have here, where you've essentially just got a list of all of the different edge lists for each vertex, or you can have a representation where you have a list of nodes or vertex objects that will hold all of their own adjacency lists. Either of them works, they're just different ways to represent a graph, but the important part here is they're specifying the order by which we need to look at the elements here. So, for a breadth first search, it utilizes a queue as its data structure for storing the vertices we're looking at. And queues are first in, first out, or FIFO. And they work much like lines you'd see in real life. Like say you've got a grocery store line, and you've got your people that lined up, 1, 2, 3, and 4. The first person who got in line, this guy number 1 here, is going to be the first person that gets their stuff processed and gets out of there. So first in, first out. And they want us to test this with 2 different start points. One where we start at vertex 3 and one that we start at vertex 4. So let's start with A, and we'll take a look at how it looks starting with vertex 3. So again, we use a queue. I'll put this here so you can keep track of it. And we'll go ahead and we'll put the first one, vertex 3, into our queue. So 3 is going to be popped out of our queue and processed. So they told us here they want us to keep track of 3 things. They want us to keep track of the current node, they're calling S, the distance from the source, and its parent, which they're calling T. So the node, the distance, and its parent. So our node is 3. The distance will probably be defined as 0 because it's at itself. And its parent, however, is kind of a vague definition. You could consider it null, or you could just say it comes from itself. It's its own parent. And we'll use that interpretation for this because that is a common one. So for our very first one, we've got 3, 0, 3. The node is 3, no distance, and it came from 3, or the start of our graph. Okay, so we'll come over here, look at the graph, and 3. So 3 can see 5, 8, and 10. And they told us that it's ordered by the numbers of the n vertices. And I'll assume he means numbered in increasing order. He doesn't specify here, but usually that's what people mean, and it's kind of implied if you don't specify otherwise. So in that case, we would get the 5 first, and then we would get the 8, and then the 10. So we're grabbing these vertices in increasing order based on their numbers. So, operating under that assumption, we will take a look at 5 now. So we pull 5 out of our queue. We visited 5, and I should probably mark here where they came from as I add them, so we can keep track of that. And how your algorithm does that is up to you, but if you need to keep track of the parents of the nodes, then you'll have to have some kind of variable associated to store that information. And for our purposes, though, well, I'll just put the little numbers here to keep track of. So 5, and its distance is going to be 1 plus the distance of its parent. So its parent had no distance from the start because it was the start. So 5 is going to have a distance of 1. And we can see that on the graph. It's got a distance of 1 along one edge. And it came from 3. So that handles the 5. And so what can 5 visit? 5 can visit 1, 4, and 8. So we'll take a look here. 1 isn't in our queue yet. So we'll add in 1 and say we got here from 5. 4 isn't in our queue yet. We'll add 4 and say we got here from 5. 8, however, is already in our queue. So we won't add 8. We won't add 8. It's already here. So that finishes everything for 5. And now we'll look at the next guy in our queue. So number 8. So 8 is going to have the same calculation for the distance. It'll be the distance of its parent, which was 3, has no distance, plus 1. So we have a distance of 1, and it comes from 3, its parent. So we look over here, we take a look at 8. 8 can go to 5, 6, and 7. 5 has already been added into our queue and process, so we won't add that one. 6 hasn't yet, so we'll go ahead and grab 6 and tell it we came from 8. And 7 hasn't either, so we'll grab 7 and say we also came from 8. Alright, 8 is done. Now we'll take a look at 10. So we've got 10 here. It's going to have a distance of its parent plus 1, and we got there from 3. Alright, so that handled all 3 of the numbers that we saw initially at our first depth. So these are all going to be our distance 1s. And 10 here can visit 3 and 4. 3 has already been looked at, and 4 has already been added to our queue. So 10 won't add anything. So 10, we just finished and we're done with 10. And we grab the next guy in the queue, which is a 1. So we throw our 1 in here. 1 will have a distance equal to its parent plus 1. So its parent was 5. 5 had a distance of 1. So now we're at a distance of 2. So we're 2 deep into our breadth first search now. And 1 again, it came from 5. We mark all this down. And now we'll take a look at 1. 1 can go to 4, 5, and 9. 4 already in our queue. 5 already looked at, 9 has not been, so we'll add 9 and tell it we got here from 5. Alright, next number is our 4. So 4 here. It came from 5. 5 had a distance of 1, so we're going to have a distance of 2. We take a look at our 4, and 4 here, it borders 1, 5, and 2. 1 already in here, 5 already in here, so now we'll just put the 2. 2 came from 4 in this case, and that finishes everything for 4. Now, 6 is our next guy, so we pull out our 6. 6 came from 8. 8 had a distance of 1, we have a distance of 2, and we came from 8. Take a look at 6 here. 6 borders 2, and it borders 9. Which are both already in our queue. So 6 won't add anything, and we're done with 6. Now we'll take a look at 7. So 7 came from 8, so it has a distance of 2, and we mark it as coming from 8. And 7 can't go anywhere here. We're totally stuck. It's in this little cubby hole. So we're done with 7, and let's take a look at 9. So 9 here borders the 6 and the 1. So 9 borders the 6 and the 1. which have both already been added to our queue and processed. So we won't add anything from it. 9 came from 5. 5 had a distance of 1. So again, we have a distance of 2 coming from 5. Actually, wait, that's not right. Why did I mark this as 5? 9, my bad. When we originally added 9, we added it from 1 when we were at the 1. So this should actually be a 1. Sorry about that. And this makes more sense. And we can see this here. We can see that the 9 actually came from the 1 because it should have a distance of 3. So let's fix that here. So 9 actually has a distance of 3, and it didn't come from the 5, it came from the 1. Alright, so yeah, I'm not sure why I put 5 there. It wouldn't make sense, actually. If you're keeping track of this, you should see that you've got all of the parents in order as they're added. So it came from 1 and had a distance of 3. So now, finally, we grab our 2. Our 2, we'll double check this one. Our 2, we said, came from the 4, and that makes sense. It could either come from the 4 or the 6, but we found 4 before we found 6, so it definitely came from the 4. And it'll have a distance of 3. We'll double check that. 1, 2, 3. Yep, has a distance of 3, and it came from the 4. So we've got our 2, 3, and our 4. And yeah, we finished. We processed all of our vertices. There's none left to add. And we found all of the vertices, their distances from the source, and their parents. And yeah, that should handle the Bradford search, where you go from vertex 3. And if you went from vertex 4, it would look pretty similar. You would put 4 into your queue to start. Here, I'll do the initial setup. So you put 4 into the queue to start, you pull 4 out, and you could say 4 with a distance of 0 came from 4, and it'll add 5, 1, and 2 in increasing order. So we've got our 1, our 2, and our 5. So 1, 2, and 5 have been added. It'll then look at 1. So 1 has a distance of 1, and it came from the 4. And again, it would probably help to mark these like this. And this will repeat much in the same manner as our previous one. Just be careful to keep track of the parents, and the distances will always be the distance of their parent plus 1. And let me know if you have any issues with that, but it should follow the same pattern, and you should be able to work through it. So let's now continue on and take a look at number 2. So let me clear out the little board here. Alright, so that's annoying, it keeps going away. Okay, so our depth-first search. So depth-first searches, these utilize a stack. Whoop. These utilize a stack, so they are first in, last out. So much like putting a stack of plates in a cafeteria, the first plate you put in is going to be all the way at the bottom, and it's going to be the last one that comes out. So it's buried under all the other ones. The very last plate you put on is going to be the first one that comes out. So the first one that goes in, this plate down here, is going to be the last one you actually pull out. So let's draw out the information for this one. So we've got here, for the following diagram, give the result if depth-first search applied to the following graph in the form of sequence of vertices as they are discovered by the algorithm, where each vertex is given by its parent name, discovery time, and finishing time. So there's going to be 4 things: the vertex, the parent, the discover, and the finish time. And so for example, ST24 should mean that vertex S was discovered from vertex T at time 2 and finished at time 4. Assume adjacency-less representation. As prescribed by depth first search, you should start with the first vertex in the adjacency list. Okay, so same idea here. We have an adjacency list and we want to visit it. In this case, instead of in increasing order of the numbers, it's going to be an increasing alphabetical order. So let's give that a try. And technically S comes way after A, but I think they're using the special S here to signify this is where they want you to start, especially since it has no incoming nodes. So operating under that logical assumption, we'll say that S is the very first node that we're looking at. So S is our first node, and its parent, again, in this case, you could say no parent or just itself. And now, for depth first search, we're going to keep track of a discovery and finishing time, which basically correlates to your timestamps while you're running the algorithm. So for our discovery, it's the very first thing that happened, so a timestamp of 1. And it is going to see, it can see A and B, and we want to preference the lower alphabetical order, because they said it's ordered in alphabetical order. So we would take a look at A next. So we would come down here, and we're taking a look at A. So A has not been added yet, and we'll keep track of our nodes here so we know whether they've been added. So we've got A, and so node A, it came from S. I'll go ahead and mark these so we can keep track. And it occurred at the second timestamp. And you'll notice I haven't added the finishing times yet because we haven't finished with these nodes. Node S still has children, node A still has children. So we haven't finished processing these nodes yet because there's still more information we could garner from them. So A can visit C, B, and D. Those are its three children. And since we're preferencing alphabetical order, B will be the one that we look at. And we'll say it came from A, because we got to B from A. We'll mark this down. B came from A, and it was the third thing we did. So we'll take a look now at B. B can go only to E. E is its only one we can go. We'll mark this down. So we went to E from B. So here we go at E. We got here from B. And it had a timestamp of 4. All right, same idea. We're at E now. We look at where we can go. We can go to F, and we'll say we got to F from E. So F came from E, and it was at timestamp 5. So we're taking a look at F here now. F can't go anywhere. It's got no children. So we're going to be done with F now. It has nowhere to go. So it'll have a finishing time now of 6. So it's the sixth kind of execution in our algorithm. And it's all done. We're completely finished. And now we're going to backtrack up to our E. Our E, it can only go to B. It can only go to B, which has already been checked, added to our stacks. We don't do that. E is now done as well. And I probably should mention, when we first got to E, we could have actually also looked at B. I just immediately went to F because B had already been added, but that is something the algorithm would check. It would check both B and F, and it would say, okay, B's already been in our stack. We won't add B, and that's why it went straight to F. So E has been finished. We backtrack again now to B. Where can B go? B can't go anywhere else, so it's also done. So B is done at timestamp 8, and yet again, we backtrack, and now we're back at A. A now has valid children, though. It has C and D, and we're going in alphabetical order, so we're going to grab C and say he came from A. So now we're going to move down and we're in C. So C came from A, and now it was at timestamp 9. You have to be sure that you always add 1 to the timestamp. So it wouldn't be 7 or 6, even though that was when our last finishing time was. It's going to be after whatever the last number you wrote. So it'll have 9. And so what can C go to? C can go to D. So we've got D here that came from C. We'll mark that down. We've got D coming from C at timestamp 10. So now we're in our D. D can go to B and G. And again, similar example, we won't go to B because B's already been added to our stack before. So we'll go to G. So we've got our G coming from D. So we'll add this here. G came from D, and it happened in 11. So now we take a look at G. And G can only go to F, but F has already been processed and is all done, so we won't go there. It has no other children, so we have to backtrack, and we're done with G. So we come back up to D. D has no other valid children, so it's done as well. It's all finished. We step back up again to C. C has no other valid children. It's done. We step back up to A. A has no other valid children. It is done as well. And finally, we step all the way back up to our original S. S has nowhere else to go. It's done as well. And we finish at timestamp 16. So, and 16 is good because we notice we have 8 total vertices. So we would expect, if they are all visitable, to have double the number of vertices as our total number of times. So we have 16 total times with our 8 vertices, with a discovery and finishing time for both. So that should handle the alphabetical order. And the reverse alphabetical order will be pretty similar. Again, I'll do the initial setup here. So going in reverse order, we grab our S, and our S looks at its 2 children. It sees A and B, and this time we'll go ahead and grab B, saying it came from S. And we'll have a very similar start. S came from S with a initial discovery time at 1, and then B came from S with an initial discovery time of 2. And then we look and see what B can see. B can see E, so we grab E coming from B, and as you can see, this will look remarkably similar. So apply the same logic we did here, following reverse alphabetical order, where we always go to the largest letter, or the furthest letter in the alphabet, rather than the previous ones. And we'll follow the same general execution. And again, let me know if you have an issue with that, but I think you should be able to do it in reverse alphabetical order now. So let's take a look at the next one. Number 3, give an example of a DAG. So a DAG is a directed acyclical graph with at least 4 vertices that has a unique topological sort. Okay, so with a unique topological sort, I assume they mean that it only has one valid topological sort that includes all of the vertices. Again, this is a little vague because a DAG could have multiple unique topological sorts, but I think what they mean is that only exists one topological sort that's valid. And it needs to have at least 4 vertices. So for that to work, and if there's only one topological sort, you have to be careful of how it's structured. And so an example here that could work is we've got our A. It goes to our B, which goes to our C, which goes to our D. So here, there's only one potential sorting. You can go A to B to C to D. And there's no other valid topological sort that'll include all of these nodes. If we start at B, we can't get to A. So we would only have B, C, and D. And likewise, if we start in any of the other nodes that aren't A, we're not going to see all of the vertices. And there's no choices here. You can think of whether there's unique topological sorts as to whether following through this graph you ever have any choices of paths. If you say there was a line here from A to C, then there's different potential paths we could take. We could go A to C to D, or we could go A to B to C to D. And you also have to be careful not to have cycles, because if you have cycles, then it's not a directed acyclical graph anymore. So we would want to not have choices and have a nice little 1 to 1 to 1, where there's only one node that doesn't have incoming nodes. Again, if there was a line here, now we've got a cyclical graph. So this should be a simple example. It gives us a unique sort. We've got A, B, C, D. That's the only path that we have in our graph. So let's take a look at the number 4 thing here. Given a connected undirected graph, is there a vertex in G such that it can be removed, but G stays connected? If so, explain why, and give an algorithm that returns this vertex. All right, so they want, let's see, let me draw a little graph here, see if they let me undo this all. Perfect. All right, so you've got a nice little graph here. You've got, say, A, that's poorly drawn. You've got A, B, and they said undirected, so we don't need lines here. So C, D, let's grab one more, E. Okay, so we've got our vertices A, D, E, B, and C, and they want to know if we can remove a vertex and have this graph still remain fully connected. And fully connected means that we can get to all of the other nodes. And since it's undirected, we would need to get to any of all of the other nodes from any node. So if we start at A, we need to be able to get to all the other nodes for it to be fully connected. If we had good old F all the way out here, not connected to anybody, well, we can't visit it. So it's not a fully connected graph anymore if it includes all of these vertices. So assuming no F, right now it's fully connected. So we have a connected undirected graph right now. And if we removed vertex C, so we just had A, B, D, and E, it's still fully connected. All of the vertices in our graph are fully connected. However, if we removed B and thus removed its all lines connected to it, C is now all out here on its lonesome, and we no longer have a fully connected undirected graph, because we've got this node C here that can't be visited if we start in any of these 3 nodes. So they want you to, so that's how you would have an example where removing a node causes the graph to become no longer fully connected. And D would function the same way. If we remove D, then E would be jettisoned from our connected components, and we'd no longer have a fully connected graph. And here they're asking if you can give an algorithm to find such a vertex, that if this vertex were to be removed, we would no longer have a fully connected graph. And they give you a hint here. Think breadth-first search or depth-first search. So if we ran breadth-first search on this graph right now, we'd be able to visit all of the nodes. We would see A, B, C, D, and E. All of these nodes would be found in a breadth-first or depth-first search. And so we know that it's fully connected because it found all of the vertices. However, if we give it a try, let's say we remove C from our graph and all of its connected lines. So right now C has been removed. and we run depth first search on this graph, we would get the A, the B, the D, the A, the B, the D, and the E. So we would get the other 4 nodes still, because if we ran our depth first search, we'd still see them all. So if we remove a vertex and then run a breadth first or depth first search, and we find all of the remaining nodes, then we know it's still fully connected. If, however, let's see if it lets me undo this enough. If, however, we cut out B from this graph and we run a depth first search on it, starting at A or starting at C, we would only find 1 or 3 nodes. So assuming we started A, we would find A, D, and E. If we started at C, we would find only C. So in this case, if we remove a vertex and the number of vertices we find, let's say the number of vertices currently is n, and in our example right now we've got 6. So if we remove one of the vertices, so if we only have 5 vertices, there's now n minus 1 vertices, and we run depth first search, we should find n minus 1 vertices. In this case, when we removed a node that caused it to no longer be connected, we're getting less than n minus 1 vertices. So it looks like we simply remove a vertex, run depth first search, and see if we now see n minus 1 vertices. If we do, it's still fully connected. If we see less than n minus 1 vertices, whether 1 or 3 or any number that's less than n minus 1, then it's not connected. Then it's no longer a fully connected graph. And you could simply test this with all of the vertices. We try getting rid of C, we run depth first search, and we see if we get n minus 1 or less than n minus 1. Oh, I'm sorry, I did the wrong way. We want to have a value that's less than n minus 1. So n minus 1 is greater than the value. So if we end up getting that, then it's not connected. If, in this case, we only get 3 or 1, it's not a connected graph. And so that should work. You just test it on any of the vertices. If they give you n minus 1, they are vertices you can safely remove without disconnecting the graph. If they give less than n minus 1, then they are not vertices you can safely remove. Okay, well that should handle pretty much everything you need for this homework, I think. Let me know if you have any questions, but hopefully you should be able to implement the part B's of these, where there's the slight variation based on what I did. But let me know, and I hope this helps. Have a good day.